Hey there, so previously I've made a video about finding the center of mass, which is this page right here. So what you have noticed is that the center of mass it's in the body, but at the same time the center of mass can be outside of an object, outside of the body. So this video will be more complicated, but it's still the same, okay? The concept it is still the same. So let's get started. So let's say I have a hollow tube, a metal tube, which is like this, right? This hollow tube, okay? So if I cut this part right here, I want this part, I do not want this part. Okay, so my hollow tube will be like this, right? After I've cut it, will be like this. But this hollow tube, it's thick. It's a thick hollow tube, okay? So it's look like a donut, okay? So right now I want to find the center of mass of this hollow tube, this donut shaped hollow tube. So I'm going to hang this thing, and I'm going to hang this object on a beam or on a wood. And this part right here, I hang it with a pin or nail. This will be our torque, okay? So we know that center of mass, let me just move this thing a little bit lower. Okay, so I just want to quickly explain it. So the center of mass causes no turning effect. Okay, so no turning effect means no moment, right? The formula T E equals to F times perpendicular distance will be 0, okay? 0 F times no distance means that there is no turning effect, 0, 0, okay? So after I've hanged this object, I can draw a line. I can put a string tie it up, and I will put a heavy object here, okay, a heavy object. So like this, I can draw a line, okay? So I'm just going to name this point as maybe as again A and B. Like our previous video, I put it A and B. So I will start with A and B, then we will go on with C and D with my another diagram here. So after I have hung this object, I will change my position, okay? So let's say I hang it like this, okay? So this will be our torque, and again I will put a string here. So just now this is A and B, right? So the A and B will be like this. Okay, A, B, then C and D. This will be our new point, our C and D. And I will draw a line here. This represents the line. So how do I find the center of mass is that the line from this first diagram, I'm just going to name it as 1 and 2. The line from the diagram 1, it's here, right? Okay, so the center of mass, it is, let me just change to maybe green color. So this is the center of mass, okay? Center of mass. Okay, so this will be our torque. So the reason is simple. The reason is simple. Look at this equation right here. When there is no perpendicular distance, which means there is no, let me just roughly draw it, the torque right here, right? So this will be our center of mass. As you can see, there is no distance between the center of mass and the torque right here, like this. So just now is A and B. Okay, so A and B, and this is the line, right? The line, and the center of mass, it's here, okay? It's here. So there is no perpendicular distance. If my A is here, my center of mass is here, this we call it as line of action. So there will be there will be distance. Okay, this will be our distance. So let's try another example to strengthen your foundation, to strengthen your knowledge of center of mass. So this is our center of mass. Okay, let's try another example. So the center of mass can sometimes act like a pivot or torque. Okay, so not to get confused between pivot and torque, so let me just show you a quick one. This is a metal bar. If you apply a force here, there will be turning effect, right? The movement will occur here, but this is a torque. Okay, and the pivot, this is the pivot. Okay, this is the pivot. Okay, so if you apply a force here, the moment will occur here. Okay, let me just erase this, a quick one. Okay, so to sum up, pivot is equals to moment, okay, and torque is equals to moment as well. Let me just show you in a Venn diagram. This is a circle. This circle represents the moment. Okay, and this one is the pivot and the torque. Okay, moment means turning effect, and the pivot, which is the point of rotation like this, it's like a point. Then there is moment if there is force applied in the object, and the torque is almost the same as the pivot. It's just that pivot usually it's like a point, it's like a dot right here, it's like a very sharp point, and usually torque it's like this. Okay, so yeah, like this. So let us just try another example. So this time let's try an object like this. It's like a square C shape. Okay, so if we hang this object, if you want to find the center of mass, first if we hang it like this, if you hang it like this, if this thing, the center of mass of this object, this, let us just call it as object A. Okay, this object A, if the center of mass of the object A it's here, and the torque here it's here, and the perpendicular distance, if there is perpendicular distance between the torque, the line of action, and the center of mass, there will be turning effect, because because turning effects are because the formula of turning effect or moment, it's equals to force times perpendicular distance. If there is distance, there is turning effect. So this object, if we hang it like this object A most likely to have a clockwise turning effect. Okay, so let us just name this as diagram 1. Okay, so in diagram 2, it's the same thing. So we'll have the turning effect of clockwise movement, right? So this thing will be like this. Okay, let me just draw it bigger. Like this. If this is the torque it's right here, and the center of mass it's right here. Okay, and there is no perpendicular distance. Okay, let's say the center of mass it's right here. Okay, but I can do it without the center of mass of this thing. So the center of mass is right here. It's somewhere in this line, but I do not know which point it is. And for the diagram 1, let me just erase the center of mass as well. Okay, so we can do it without the center of mass, because in the end, we still be able to find the center of mass. So after this diagram 1, we will have a clockwise turning effect. It will be like this. It will slightly shape it like this, okay? A clockwise turning effect. From my perspective, if I look at it like this, we have a clockwise turning effect and like this. So if we draw a line like this, I will just call it as A and B again. So we know the center of mass or the center of gravity, it's on this line, but we do not know which point. So let's do another test. So let's say this time, let's hang it like this. Let's hang it like this. Okay, this will be our torque. So I will draw a line here, here, and I will name it as point C and D. And this A, it's right here, and B. Okay, so just assume here we have drawn a line here, so the line will be here somewhere here. Okay, the line will be here, and as soon as the point CD, the line CD have crossed the line AB, this will be the center of mass or the center of gravity, which I will call it as COM. Okay, so this will be our center of mass. So this will be our center of mass, in short form COM. Okay, so in the previous video, I've talked about why the center of mass have always tried to have a turning effect. The reason it's here, the formula. So as soon as the center of mass always tries to make no perpendicular distance between the line of action. So in this case, this is the line of action. We call it as line of action, CD. So this will be our line of action. If AB, this will be our line of action. So there is no distance, no perpendicular distance between line CD and line AB. Okay? So that's it for this video. I will see you in the next one. Bye.